Our last video introduced orthogonal families, and we left off with this example. The functions 1 cosine pi x over L, L is your favorite positive number, sine pi x over L, cosine 2 pi x over L, they form a pairwise orthogonal infinite list of vectors, meaning if you take any two functions on this list, multiply them, and integrate from negative L to L, you should get 0. This is actually a very important example, as we'll see going forward, so I wanted to use this video to explain why they are pairwise orthogonal. The reason comes from this differential equation I've written down. Y double prime is negative this constant times y. I also wrote down some other conditions. It's not difficult to check that both functions of the form cosine n pi x over L and sine n pi x over L satisfy this differential equation. You could take two derivatives and verify that this is the case, and similarly you can plug in negative L and see it's the same as if you plugged in positive L to both the function and its derivative. So I'm going to use this differential equation to prove that they're pairwise orthogonal. So suppose we have two functions that satisfy something like this. So suppose we have y1 double prime is negative n pi over L squared times y1. So y1 is a solution to this differential equation. And similarly, y2, but for y2, I'm going to not have n, but possibly a different constant, m. So y2 double prime is equal to negative m pi over L squared y2. What I'm going to do is take this first equation and multiply by y2. So I'm going to multiply this by y2, and I'm going to take this second equation, and I'm going to multiply both sides by y1. Then I'm going to subtract. So the technique is, again, I'm going to multiply this first equation by y2, the second equation by y1, and then take the difference of the two expressions. So if I do that, I think I'll get y1 double prime y2 minus y2 double prime y1, and that should equal m pi over L squared minus n pi over L squared times y1, y2. Next, I will integrate both sides on the interval from negative L to L. So the integral from negative L to L on both sides gives me y1 double prime y2 dx minus the integral from negative L to L y2 double prime y1 dx. And just so I don't have to keep writing this long expression down, I'm just going to put c. It's some constant, so that's my constant c here, times the integral from negative L to L of y1 y2 dx. So this side I'm going to integrate by parts. Each term I'm going to integrate by parts. Now when you integrate by parts, you get to differentiate one function and integrate the other. So for this first integral, it seems natural that I will differentiate the y2 and integrate the y1 double prime. So on the side here, I'm doing integration by parts, differentiating the y2 term, integrating the y1 double prime, and this first integral becomes y2, y1 prime evaluated at negative L and L. Then I get minus the integral from negative L to L of y2 prime y1 prime dx. And then I could do the same thing for the second term, except reverse the roles of y1 and y2. So I will get minus y1, y2 prime evaluated at negative L and L. And that would be plus the integral from negative L to L of y2 prime, y1 prime dx. And all of that should still equal a constant times the integral from negative L to L of y1, y2 dx. You could see that this term and this term are the same, except with opposite signs. So those cancel. And then furthermore, when I plug in the conditions at negative L to L, here, let's see. This part would be y2 at L, y1 prime at L, minus y2 at negative L, y1 prime at negative L, and I get a similar expression here. I don't think I'm going to write that down, but that's all equal to a constant times the integral from negative L to L of y1, y2 dx. But if you use these conditions up here, they say that y2 of L is the same as y2 of negative L. So this could be turned into a plus. And similarly, this second condition says the same property holds for the derivative. So y1 prime of negative L is the same as y1 prime of L. That could be turned into a plus, and these cancel. So in other words, this whole side here is 0. Therefore, the integral of the product of y1, y2 from negative L to L is 0. And that's exactly what it means to be pairwise orthogonal. So this means that the inner product of y1 and y2 is 0. Since y1 and y2 could be anything on this list, since y1 and y2 could be cosine n pi x or sine n pi x over L, I'm done. I'm done. Okay, excellent.